In this section, we want to be able to do two things. First, we want to be able to use the direct comparison test to figure out whether or not an infinite series will converge or diverge. And we also want to be able to use the limit comparison test. So we're going to learn about two more tests that we can use to determine whether or not a series converges or not. And this section is all about comparing series. So we start off with a conversation about looking at series that are similar to each other. For example, the series on the left here, 1 over 2 to the n, I look at that and I know that that is a geometric series. If we think about what we know about geometric series, we know that this series definitely converges because the absolute value of r in this case is the absolute value of 1/2, which is less than 1. I also know what this series converges to. It converges to a over 1 minus r, which in this case would turn out to be 2. But the series on the right side that looks very similar to this series, this is not a geometric series. Simply because of the n that shows up in the numerator. So just adding that n to the numerator completely throws off that this is no longer a geometric series. I cannot say what r is. I don't know if this series converges or diverges. But the idea behind this lesson is that you could compare this series to a geometric series. And that's what we're going to be doing. Similarly, in the second row, the series on the left, hopefully you can identify that as a p-series. In this case, p is equal to 3. The criteria for p-series to converge is that they converge when p is greater than 1. And so I do know that this series converges. The series on the right side, however, this is not a p-series. Simply because of the +1 that shows up in the denominator. It's very similar to a p-series, but it's not a p-series. Those denominators are not the same. In fact, the denominator on the right side, this denominator of n cubed plus 1 is bigger than the denominator on the left side. And bigger denominators mean smaller numbers. So this is smaller than the p-series on the left side. That'll come up again and be relevant to help us figure out whether or not that series converges, because we will compare it to a p-series. And then finally, in the last row of this table, the series on the left, when I look at that series is something that is easily integrable, the terms of that series, because just looking at this expression in here, I could integrate that rather straightforwardly with a u sub. Hopefully, we could also prove that that function was continuous, decreasing, and greater than 0, positive, so that we could use the integral test to determine convergence. However, the series on the right side, this is not as easy to integrate, but we could compare it to the series on the left side. So now that we've seen how slight variations, making a very small change, something as small as adding n to the numerator or adding a 1 in the denominator or just squaring an n that was in the top already, can change a series and can also change whether or not you're able to use one of the tests that we have already studied. So now let's go learn some new tests. The first test we're going to talk about is the direct comparison test. The idea behind the direct comparison test is that if you can find some series, b sub n, that you know converges, and then you look at another series where the terms are a sub n, this condition here says that the terms of a sub n are smaller than the terms of b sub n. I'm going to write that off to the side here. A sub n is a smaller sequence. So if B sub n converges and B sub n is bigger than A sub n, then it must also be that A sub n converges. Because if I add up B1, B2, so on and so forth, infinitely many terms, and I'm able to get a finite number, and then I take the A's and I add them up, well, all of these A's are less than the B's. So this is also going to add up to some finite number. It's going to add up to some finite number that is smaller than what the B's added up to. On the other hand, if we start off with a sequence A sub n that diverges, so if I know that the A's add up, and let's say I know the A's add up to infinity, I know that they diverge. This is very poor notation, but I hope it helps you understand the concept. If all of the A's add up to infinity, and the B's were larger than that, in the top row, if I'm adding up bigger numbers, then the larger numbers above would also add up to infinity. So that means that the series of B sub n diverges. It is important to note that the conditions on the left, if B sub n converges, if A sub n diverges, this is something that you should already know. In order to use these tests, you have to know that there's some series B sub n that converges and there's some series A sub n that diverges before you can reach the conclusion. What's happening on the right side, this then, this is what you want to show. So we're going to have to choose series A sub n and B sub n very carefully. So for example, let's look at number 3. This series looks very similar to a geometric series where r is equal to 1/3. Now we need to figure out what is the relationship. Now, before I even say that, we also know that this series here converges. And I know it converges because r is 1/3, and the absolute value of that is less than 1. Now we need to figure out what is the relationship between 1/2 plus 3 to the n, what's on the inside of the series we're trying to determine convergence or divergence for, and the series that we know, 1/3 to the n. Depending on which one of these is larger or smaller, it's going to help us determine which one is an and which one is bn in this test. The denominator on the left side, this is a larger denominator. When the denominator is larger, you have a smaller number. A larger denominator gives you a smaller number. So this is the relationship between these two series. So what we have already is a larger convergent series. We have found a series that was bigger than the one we were working with, and it converges. So that must mean that by the comparison test, the direct comparison test, the series n equal 1 to infinity of 1/2 plus 3 to the n must also converge. So one of the ways that the direct comparison test works is you can, in plain terms, you can conclude that a series converges if you can find a larger convergent series. If you can find a series that's bigger than your series and that converges, then you can conclude that your series converges. Let's look at example 4. This looks very similar to a P series. Remember, P series look like the sum of 1/n to the p. In this case, I'm going to choose p to be 1/2 because that's the same thing as having the sum of 1 over the square root of n. Now first, let's discuss whether or not this series, the one that we know, the one that we're comparing to, does that series converge or diverge? In this case, p is equal to 1/2, which is less than 1, and a p-series only converges if p is greater than 1. And so this series diverges. Now let's go figure out what is the relationship between the series that we have and the p-series that we are comparing to. Which one of these is smaller, larger? It's helpful to compare the denominators. Again, on the left side, I have a larger denominator. A larger denominator means a smaller number overall when you actually do the division. So the inequality points that way. So what we have done in this example is we have found a larger divergent series. The series we chose was bigger. 1 over the square root of n was bigger, and we knew that it diverges. Let's see what that tells us. Nothing. In this case, when we chose this series, 1 over the square root of n, and that turned out to be larger than the series that we were working with, and that means that 1 over the square root of n was our b sub n, our larger series. And what the test tells us is that for the larger series, you can only reach a conclusion when the larger series converges. You can't reach a conclusion if the larger series diverges. So we're not able, everything that we've done so far with that series, we're not able to use this test to tell us anything about the series we're trying to determine convergence or divergence for. So we're going to need to go compare this to a different series. At this point, I think it's helpful to pause and think about, what do we suspect the behavior of this series even is? We know that the series 1 over the square root of n diverges. With that information, do we think that the series 1 over 2 plus the square root of n, would we guess that that also diverges? Or do we think that that then converges? So one way to think about this is, if this original series that we chose, 1 over the square root of n, if this series diverges, it means that the terms inside of this series are too big. Those terms are too big. So the series is diverging. They do not add up to a finite number. When we come over to the series that we're working with, the difference is now we have added 2 in the denominator. We have already discussed that a larger denominator does in fact mean that the terms are smaller. So these are smaller terms. But do we think that they're small enough to converge? I would suspect not. Because adding 2 in the denominator is not going to change things on an infinite level to make these numbers no longer too big. So I would guess that the series that we are working with diverges. I suspect that this series diverges based off of the logic that this series diverges. With that assumption, I would then be trying to use the second part of the direct comparison test. If I think that our series diverges, it would be helpful if I could find a smaller series that also diverges. Then we could compare it to that smaller series. So a series that I know diverges is the series 1 over n, because that's a harmonic series. If I think about the terms of this series, first, because I need to show that it is in fact smaller than the series that we are working with. If I think about the terms of this series, I'm going to look at different values. I'll start with n equal to 1. And then I'm intentionally going to choose values where n is a perfect square, just to help me evaluate them on the right side. So when n is 1, I would get 1 and 1/3. I substitute n equal to 4, I get a fourth and a fourth. When n is equal to 9, I get a ninth and a fifth. So what is the relationship between these numbers? Well, a third is smaller than 1. A fourth is less than or equal to a fourth. 1/9 is less than 1/5. When n is equal to 16, we have 1/16. 1/6. 1/16 is less than 1/6. So it looks like, in fact, notice right here when n is 4, I can turn it this way because they're equal. So it looks like for n greater than or equal to 4, the harmonic series 1 over n is smaller than the series we're working with, 1 over 2 plus the square root of n. So yes, we can find a smaller divergent series. We do know this index starts at 1, so I'll also start at 1. We do know that the series that from n equal 1 to infinity of 1 over n diverges. Therefore, we can conclude those 3 dots in a triangle mean therefore. You may see people write that as they're doing math, that the series we are working with also diverges by the direct comparison test. So in the big picture, what the idea is that as you take, we know that if we add up these numbers in green for the harmonic series, that these numbers diverge. This sum is too big. And we also know that as we add up these numbers in pink, look at how these inequalities go. The numbers on the right in pink are eventually bigger than the numbers in green. So if they're bigger, when I add them up, this is also too big. Moreover, it's even bigger than that green divergent series. So that's how we are concluding that it diverges. So sometimes I think it's worth it to take the time to think about the series that you're starting with. When you compare it to another series, for instance, when we compare to that P series that's highlighted in green, the 1 over the square root of n, and we concluded that that diverges, that means this probably also diverges. Let that guide how you use this test, because the direct comparison test, you're either going to reach the conclusion that it converges or that it diverges, and it depends on what you started with. So it's nice if you have an idea. Are you trying to use the first part of this theorem and conclude convergence like we did in number 3? Or are you trying to use the second part of this theorem and conclude divergence? And you can only know that if you kind of have an idea of what you want to show. If you've thought through, well, how do I think this series will behave? The second half of this lesson, we're going to discuss the limit comparison test. So the limit comparison test will come in handy when we're not able to apply the direct comparison test. Keep in mind, we can only apply the direct comparison test if we can start off with one of these two conclusions. So we have to have this relationship between the two series where we have either found a larger convergent series, or I will add this bullet point up here. We could conclude that a series diverges if we can find a smaller divergent series. So if we can't find a smaller divergent series or a larger convergent series, then we cannot use the direct comparison test. And that's when we will use the limit comparison test. So what the limit comparison test states is that if you have two series, A sub n and B sub n, both of the series need to have positive terms. The terms of the series need to be positive. And if you divide the terms of the series, take the limit as n goes to infinity, calculate that, and you get some expression L. Well, if that value of that limit is both positive so not zero, not negative, and finite, so not infinity, needs to be a finite number, then you can conclude that the two series either both converge or both diverge. So the way this test will work is that you need to pick a series that is comparable. All I mean by that is it should be a good series that you want to compare to. The same way that up here we compare to a geometric series, and over here in the fourth example we compare to a p-series. So you want to pick a series that is comparable, and you also want to make sure that you know whether that series converges or diverges. Because the conclusion of this test is that they do the same thing. So you need to know what the series that you chose, you need to know what that series does. So let's take a look at how to use this theorem. Example 5, we have a general harmonic series. The denominator here is an plus b. Remember, the harmonic series is the series 1 over n. That is the harmonic series. And we also know that this harmonic series diverges. We know that diverges because it is a p-series, and p is 1. P-series only diverge when p is greater than 1. 1 is not greater than 1. So that series does not converge. So let's figure out, what does this series do? So I'm trying to figure out convergence or divergence for a general harmonic series. I would guess that it also diverges because it looks a lot like a harmonic series. So I am going to compare this to the harmonic series. So let's take the limit as n approaches infinity. This is what the limit comparison test tells us to do. It says take the limit as n approaches infinity and divide the two terms of the series, a sub n divided by b sub n. It doesn't particularly matter which one we choose to be a sub n or which one we choose to be b sub n. But for one of these, a sub n will be the series that I'm trying to figure out. Does it converge or does it diverge? So I'll take the terms of that series and I will divide them by b sub n, the second series that I'm comparing to, which is 1 over n. So first I'll just simplify this expression, dividing these fractions, because this is over 1, and then I'll keep change flip to give me n over 1, and then I'll multiply straight across the top and straight across the bottom to get this. So the reason you want these series to be comparable is because this limit should be pretty easy to evaluate. If you chose a good series to compare to, notice that the degree of my numerator matches the degree of my denominator. So I know that this limit is equal to the ratio of the leading coefficients, which in this case is 1 over a. This a right here. Now we have to see. So this is our L. This is our L. This is what the limit was equal to. This is positive, because a general harmonic series does have a greater than 0, and it's also finite, because a is not anything other than some positive number. So I can conclude that by the limit comparison test, these two series have to do the same thing. And we knew that the harmonic series that we chose, 1 over n, diverges. So I can now conclude that the series we were working with, we were trying to figure out, the general harmonic series also diverges, because the test says they either both converge or both diverge. So first things in example 6 is that we need to find a good series to compare this to. And I will be using the limit comparison test. So when I'm trying to determine what series I want to compare to, I'm looking at this expression in here. and I'm finding the major characteristics of it. It is a rational expression, so I'll use a fraction in here. The degree of the numerator is 1, so I'll just keep my numerator 1. In the denominator, highest exponent that shows up is n squared, so I would like to capture that n squared. And everything else doesn't really matter. The coefficient of 3 doesn't really matter. The minus 4n plus 5 in the big scheme of things does not really matter. I do always try to make sure that what we are comparing to is a very simple series. A very simple series that we know convergence or divergence for. In this case, this is a p series. In this case, p is equal to 2. That is greater than 1, and so I do know that this p series converges. So I'm going to use the limit comparison test where one of these will be my a sub n and the other will be my b sub n. And it does not particularly matter which one I choose. I want to calculate L, which is the limit as n approaches infinity of a sub n divided by b sub n. Again, the nice thing about choosing b sub n to be very similar to a sub n is that when you get to this point where you're about to evaluate the limit, it should be very easy to evaluate. Making sure that I chose this n squared in the denominator is what's making sure now that the degree of my numerator matches the degree of my denominator, so that I only need the ratio of leading coefficients when I take that limit to get 1/3, which is positive and also finite. So the limit comparison test does apply, and I can conclude that the series we were working with also converges. In example 7, I want to start off with a good series to compare this with. I am going to compare this to a p series. I'm going to compare this to the p series 1 over the square root of n, which I know diverges because p is equal to 1/2, which is less than 1. And a p series only converges if p is bigger than 1. So I'm now going to look at the limit as n approaches infinity. It does not particularly matter which one you put in the numerator and which you put in the denominator. When you simplify this expression, it should be rather straightforward to calculate this limit. Again, we have a case where the degrees match up, and so I will take the ratio of the leading coefficients to get an L value that is again positive and finite. So I can conclude that the series we started with must also diverge by the limit comparison test. In example 8, I want to start off and choose a good comparable series. I'm going to, at the minimum, match the degree in the numerator and match the degree in the denominator when choosing my comparable series, which does simplify down to 1 over n cubed, which is a p series where p is equal to 3, that is greater than 1, and so we do know that this series converges. So when we go to calculate L, which is the limit as n approaches infinity of the ratio of these two series, or the ratio of the terms of these two series, I just went ahead and did my division and changed flip. Again, the degree of the numerator matches the degree of the denominator, and so we only need the ratio of the leading coefficients. We do get a value that is positive and finite. And so I can conclude that by the limit comparison test, the series n equal 1 to infinity of n squared minus 10 divided by 4n to the fifth plus n cubed also converges. In example 9, I am going to compare my series here to the square root of n divided by n squared, which does simplify to the sum of 1 over n to the 3/2. In this case, p is 3/2, which is greater than 1. And so I do know that this series converges. Let's calculate L, which is the limit as n approaches infinity of the ratio of these two series. Again, the degree of the numerator matches the degree of the denominator, and so we simply take the ratio of the leading coefficients. This limit is positive and finite, and so we can conclude that our series also converges, since the series we compared it to converges, by the limit comparison test.